Okay, let's go ahead and talk through some of the information necessary to complete Lab 8. Before we get started into the main part, the questions that you have to answer later on the quiz are based off of the phase changes section, but I want to go through the state section first. This isn't entirely necessary, but it's just easier to click back and forth between the different options and show you what they look like. So any element that's a gas, so or atom or molecule, these are going to bounce around randomly. Basically, we want to think of these different molecules or atoms as having enough energy that they can escape into the atmosphere, bounce around anywhere they want to go. If we lower that energy by lowering the temperature, then we'll notice that they don't have enough energy to flow around into the air. A couple of them kind of get bounced that way. So, random evaporation does happen, but eventually those will condense back down. But these do have enough energy to flow around past each other. So they hold to the shape of the container, stick mostly to the bottom, and then you can see they just kind of jumble around each other. If we have a solid, there's still motion in the molecules. So there's still energy because there's still a measurable temperature. But now, for the most part, these aren't going to have enough energy to go around past each other. Occasionally, you'll see ones, usually around the corners, that get wiggle enough that they can kind of bounce past one other particle. But typically, one here is not going to end up all the way around on the other side or something. Now, this isn't part of this particular lab. They don't make a mention of it. But if we bring the temperature down even further, then we can get to something called the Bose-Einstein condensate. And for the rest of this lab, I'm just going to say condensate for short. But this is beyond being a solid, so far beyond frozen that basically all of the atoms or molecules have combined to be one. There's zero energy left. So all of these have basically bound to each other in a super atom or a mega molecule, if you want to call it that way. And so when I say condensate today, that's what I'm talking about. In real life, we can't get all the way down to 0 Kelvin, but scientists can get down to billionths of a Kelvin. So 10 to the negative 9 for scientific notation. And that's close enough to see these properties. Notice nothing's wiggling, nothing's moving. That's a condensate. Okay, then for our main part of our lab, we first want to look at the default sample of neon. So just when we open the page, that's what we see. Thinking about the different phases of matter that we talked about or saw in the other tab, then we can see this isn't escaping into the air, it's not floating around the bottom, but this is a solid. If we open the phase diagrams at the side, then we can see that the red point for the conditions inside this canister are here between solid and gas. So that does mean that some of these might randomly sort of bounce away and come back down. So small nudges in temperature or pressure can actually send between solid and gas. Now, if we pump the handle a handful of times, then what I'm doing is I'm introducing more of the material, but you may also notice that I'm increasing the temperature here. And doing this a handful of times, the exact number is not super important, then I'm going to create something that's going to settle into a liquid. If I do it a whole bunch of times, I may end up accidentally turning it into a gas. But you can see now that these are flowing around past each other. It's not holding its shape anymore. But also, for the most part, most of the particles don't have enough energy to escape into the top part. So looking over here makes sense because the red dot is between liquid and gas, and we can see mostly liquid molecules with some gas particles. Okay, and then if we take this and we cool it all the way down, then given the previous explanations, you can see what's happening. So the first thing, this is now frozen, so notice it all holds its shape, but they're still wiggling. If we keep cooling it down, then we're lowering the energy, we're lowering that movement, and eventually it'll bind up entirely. And so remember, we call this a condensate. It's no motion at all, it's basically one superatom. Okay, and then if I do pretty much anything to this, then I'm going to introduce more temperature, more energy, and we'll see a phase change again. So, looking at the phase diagram before we take this option, we're all the way down in the corner, zero temperature, zero pressure, nothing measurable, basically just one giant blob of material. And give it a small kick. And so now this has come back to be a solid. It keeps its shape. It's a weird shape this time, but notice the molecules aren't moving around past each other. It does have motion because it has measurable temperature, so this is a solid. Okay, and then if I heat this up, we're trying to see, all of our main options. If I heat it up a little bit, then eventually I can get to a liquid where these are flowing around past each other. And if I keep heating it up, then you might already be able to guess what's going to happen. That's probably enough. You can see that this is mostly gas. So you can see on the phase diagram, this goes all the way to the far end. We're going to pretend for now that this sort of green region is just part of the line for gas, and so this is mostly just a gas. This technically some funny behavior that can happen there, but most of the behavior that we can see is like a gas. You can also see that we do have pressure now. Pressure happens whenever there's enough energy for the molecules to knock around and bounce off of the container. So that's why the number's kind of changing randomly, is that with these collisions with the outside of the container, it's registering something in the program and causing pressure. Okay, so let's reset. Let's look at argon this time. And so for right now, the only real change is these are pink. It's got the same basic shape. I think the temperature is a little higher. But these are vibrating, they're holding their shape. So again, we see something that's a solid. If we warm this up a bit, so let's do something like maybe 70. That's probably enough. We can see that these are wiggling around past each other. Yeah, 80 might be a little bit better. But you can see that we're between liquid and gas here. And so these molecules are flowing around past each other to keep into the shape of the container. Only a small number of these are bouncing around as gas particles, which again makes sense because we're technically on the boundary between those. Okay, so if we take this now and we cool it down, then you can kind of see different shifts in the molecules and they sort of lock into place. So that's now a solid. If we keep cooling down, you might already be able to guess, but as we lower the temperature further and further, we have less and less motion until eventually we have none at all. Temperature and pressure are related to each other. So you may notice that as I lowered the temperature, the pressure came down because these didn't have enough energy to knock around into the container anymore. But here I am at 0 Kelvin, and we've got a condensate again, basically one super atom of all of these things combined. All right, and then let's send it back the other way. If we bring it to 200 Kelvin, so if we make this considerably warmer, then I think you might know what's coming. But these molecules now have enough energy that they basically can't be held down, and they're going to knock around randomly all over the container. So this is a gas. All right, let's look at something similar for oxygen. So if we reset and we look at oxygen, oxygen is a diatomic molecule. So two oxygens typically are going to be in a pair, but that doesn't really hurt what we're trying to do here. Right now we can see that this is in a solid. It has some temperature here. There's motion, but they're holding their shape. If I just immediately start to lower the temperature, then once more you see that they wiggle less and less until eventually there's no motion at all right here, and we're back to a condensate. Now, this next part is really difficult to do. I may have to try more than once on this. I want to give it a small nudge with a very small change in pressure. So I want to use this lid and I want to just barely bump these. But if I bump it too much and I give it too much energy, which I think I did, but just barely. So let's try it again. But I wanted to give it just a tiny, tiny nudge, the smallest amount of additional energy that I can. This is actually slightly easier when it has a weird shape, because that way you're not knocking into as many atoms at the same time. So let's try this again. I want to give just a tiny nudge. I think I gave it a bigger nudge. All right, hold on. One more try. Third time's the charm. I think we'll get it. All right, the main thing that I want to do here is I want to give this just a tiny nudge. I only want to give it a little bit of additional energy. And that way we're consistently getting the same answer and we're looking at the answer choices. If I hit it too hard, you may have already seen it bumps all the way into liquid. You can hit it and turn it into gas. If you hit it and hold it down, then you can even actually go off the chart. But that's what I was going for. I finally succeeded. So with a very small nudge, you can see that we're still over here between solid and gas. This is basically holding its shape and it's just wiggling slightly. So with a tiny nudge, we do get a solid. Okay, then one more element, if we take a look at water, so we'll reset, we'll turn to water, that way we're in our base conditions. And if we cool it all the way down, I hope it's not a surprise by now, but we're lowering the temperature, we're lowering the motion, and eventually we will get a condensate. And so, I tried to drill in the point to help people remember, but every different element that we've had that we've cooled down to zero has turned into a condensate. So we think about it, anything that's at 0 Kelvin will end up being a condensate. Because you get to the point that there's no more motion left, there's no more energy, and you just get a giant bonded supermolecule from any of these. That temperature, the theoretical minimum temperature, is called absolute zero. You get down to the point you can't go colder because you've already stopped motion entirely. And so even if you were to find some different way to move around, you can't have negative Kelvin. It becomes motion again, it becomes temperature, and it becomes positive Kelvin. So absolute zero is 0 Kelvin, it's the minimum temperature. In Celsius, it's negative 273.15. So depending on the source, sometimes you'll see the decimal on there and sometimes you won't. Okay, then a few more questions just about general stuff, and then the lab will be done. So an increase in volume will generally decrease pressure. These things move opposite ways. We saw this in the other order. So as I'm decreasing volume, smaller volume made a higher pressure. So notice that there's an increase there. And so if I keep bringing this down, so decreased volume, increased pressure, they're moving opposite ways from each other. And so now if I increase volume by bringing this up, an increase in volume will cause a decrease in pressure. Notice at the same time though, that when I was increasing the pressure, so as this number is going up, look at what's happening to the temperature. So an increase in temperature causes an increase, an increase in pressure causes an increase in temperature. But it does also work both ways. These move with each other. So if I start to raise the temperature, now unfortunately these are slightly random, but we were having numbers right around 70, and then as I'm raising the temperature, these are bouncing around more and more and more. Sometimes it takes a little while to have an appreciable difference. Then now you can notice that the pressure is bumping into the 80s, almost to the 90s. There's 100. So an increase in temperature will also increase the pressure because the molecules are moving with more energy. They're more likely to bounce around and hit the container and create pressure. Then final question. Unfortunately, if temperature and pressure feedback without control, because temperature can increase pressure and then pressure can increase temperature, and then they just kind of go back and forth with each other. Eventually, you're going to have an explosion. All right, then that's it.